welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am from Department of Computer Science, Alibhat College, University of Delhi. So presently we are learning about B trees, and in our inception lecture about B trees we have seen what actually a B tree is, what do you mean by its order, and what is the basic motivation behind using or behind creation of B trees. So in this lecture we will be moving forward onto this line only. We will be looking into some applications, advantages, disadvantages of B trees, and then we will try to cover some of the operations on B trees. So when we talk about applications of B trees, in the initial lecture also we have discussed that these B trees are basically used in large databases to access the data stored on the disk. When we are looking for the data that can be achieved or that can be accessed in a significantly less time, that can be done with the help of a B tree. And with the indexing feature, multi-level indexing can also be achieved with the help of these B trees. If we look into the more applications of these B trees, most of the servers also use the B tree approach. B trees are also used in computer-aided designing CAD systems to organize and search geometric data, because that data is actually huge, we can say. Moreover, B trees are also used in other areas, not only in CAD but other areas like NLP, natural language processing, computer networks, and cryptography, to name a few. Now, when we talk about the time complexity, they have a guaranteed time complexity of order log n for basic operations like insertion, deletion, and searching, which makes them suitable for large data sets and real time applications. Now, this order log n may or may not be guaranteed with the help of a binary search tree. If your binary search tree is skewed, then your search times can go beyond the order log n thing. Now, is it only kind of fair to discuss the advantages? There are some disadvantages of B trees as well. They are basically based on they are concerned about the disk based data structures, or they are actually disk based data structure. They can result in a high disk usage, which is not we can say optimum, or which is not best for each and every scenario for all the cases. Let us say we have a small data set, then the search time in B tree might be slower as compared to the binary search tree, as each node may contain multiple keys. So, it is not suitable for small databases also. So, this was actually kind of theoretical concept. We understood that what actually a B tree of order m is known and what are the properties of this B tree of order n. Now, let us try to explore some of the operations, some of the basic operations which we do on the general data structures is search, insertion, deletion, and traversal. So, search, if we talk about the time complexity for B trees is order log n, then insertion, if we talk about again order log n, deletion is also order log n operation, and if we talk about traversal of the tree, then this is going to be order n. So, n is actually we can say the number of nodes here, which is the general scenario. Now, let us try to see how this search operation in B trees is going to be accomplished. Now, B trees you also know are first of all they are self balancing trees, and apart from being self balanced trees, they are also search trees. So, search trees then the search process is going to be similar to the search in the BST, which is binary search tree. Now, let us say we have k to be searched, then we will start from the root and then we will recursively traverse down depending upon the key to be searched is actually greater than or lesser than the numbers in the node. So, for every visited non-leaf node, if the current node contains k, then we are done. So, the first advantage here is the key of the B trees may not be always on the leaf nodes, as in the case of binary search tree we can have it in the middle way also. So, if the current node contains k, you are just going to return the node, otherwise we will be determining the appropriate child to traverse with. So, that is the child just before the first key greater than k which you are looking. So, we will be looking for the first key which is greater than k, and the child which we want to traverse is just before that. And in this traversal process, if we reach a leaf node and do not find the k in the leaf node, then we will be returning null. So, this is actually, if you can see, this is similar to searching a binary search tree, and the algorithm very swiftly goes with the recursion. At each level we are optimizing a search as if the key value is not present in the range of the parent, then key is present in another branch. As these values limits the search, they are also known as limiting values or separation values inside at each level. And if we reach a leaf node and do not find the desired key, then it will display null obviously. So, this is actually a fashion which is similar to searching elements in a binary search tree. So, here we have a tree which is having 3 levels. So, the first level is the root level 100, and then the numbers are arranged in the search tree fashion, and if we want to look for 120. So, when we compare 120 with 100, we are sure that we need to go down to the right side. On the right side, if we are going to compare 120 with 130, which is the first one, then it is going to show us the path on the left of the 130 value, because 120 or k is less than 130. That means if available, it will be available inside the left node or the left the branch of 130. So, 130, and then traversing down we will be looking into 110. So, no match, and then the next the key in the tree is 120. So, in this way we are going to we can say look for a particular node, look for a particular key. Now, let us try to understand the structure of node, and then maybe the algorithm which is kind of which is used in order to search this any particular key in B tree. So, let us say we have a struct node. So, integer n is the number, integer key which is there for max keys, max number of keys, and node pointer child which is an array to the pointer of max children, and then there is a bool leaf. And this simple thing, if you can see, we have x which is less than n and greater than I, and so on and so forth. So, all these kind of we can say programming we can do as we kind of did in our binary search tree searching. So, search is actually we can say a very trivial process if we talk about the this B trees. So, search is fine because that is a search tree. So, search goes in an standard manner. If we talk about insertion, so the first thing which is going to be very important in case of insertion is the property that a new key is always inserted into a leaf node. And in order to insert a key, we need to start from the root and traverse down the tree until we reach the appropriate leaf node. That means we need to first look for, or we need to first search for the appropriate we can say the position of the key k to be inserted, and once we have found that position, the key will be added to the leaf. Now, but if we talk about B tree, we have a predefined range for the number of keys a node can hold. Now, we need to, before inserting a key, we need to check, we need to ensure that the node is having enough space and it is not crossing the maximum limit of the keys it can hold. So, that means if the node is full, then we cannot insert the key. So, if the node is full, then there is an operation which is called the split child is performed to create the space by splitting the node in two, which is the full node. Now, let us say let us try to understand this with the help of an example. Here we have a B tree of order 2. Now, as per the order 2, you can determine the maximum number of children one node can have, the maximum number of keys one can have, even the minimum number of keys a node should have. So, for example, let us say we have a situation, we have 2 as the root node, 1 on the left and 3 and 4 on the right side of 2, and we want to insert 5. So, when we insert 5, that will be inserted in the right side node, which is 3, 4, and after that 5 should be inserted. But the tree is of order 2, that means keeping 3 keys in a node is going to be kind of an overflow. So, if this is an overflow, or we can say the node 3 and 4, the node containing values 3 and 4 is full and we cannot insert 5 over here. So, in this situation what we need to do, we will be splitting this node having these values 3, 4, 5, and what will happen, the value which is going to be the median value, that means the mid value, will be kind of taken upwards. So, now your 4 is going to the root node, the root node will now contain 2 and 4, and on the left side of 2 we have 1, on the right side of the 2, left side of the 4 we have 3, and on the right side of the 4 we have the value 5. Now, insertion of 6, this it is going to we are going to split the node because the maximum keys. So, let us try to trace it again. So, we have 2 the root node, then 1 and then 3 and 4. So, if we are going to insert 5, that is instead the insertion of 6 is going to split the node. So, 3, 4, 5 we have 3 we can say 3 keys in a node, which is the maximum value. Now, if we insert the value 6, then this is going to cause a split from the middle, and split from the middle, that means this 4, or we can say either 5 also, the 4 value will be taken onto the next level or the level up, and now we have a node which is 2 and 4, that is the root node. So, 1 on the left side of the 2, 3 in between 2 and 4, and on the right side we have 5 and 6. Now, let us say we are going to insert 7. So, 7 can be inserted because it is not crossing the maximum number of values. My apologies for the first step here. Then even if we insert one more key, let us say which is 8, then what will happen? This 5, 6, 7, 8. Now, this is going to give you an overflow situation. So, we have 5, 6, 7, 8. We are going to take the middle value as we did in the third step. The middle value 6 is going to go up inside the root node. Now, root node is having 2, 4, 6. The left of 2 is having 1. The left of 2 and right of the right of 2 and left of 4 is having 3. Then 4, 6, in between 4, 6 we have one value 5, and on the right side of 6 we have 7 and 8. Now, if we insert 9, what will happen? We are going to insert 9 in the rightmost node, which is 7 and 8. Now, we have 7, 8, 9. Fine. So, 3 keys can be there because order is 2. Now, if we talk about the next insertion, which is 10, what will happen? Now this is going to be a very, we can say peculiar case, because this is going to increase the height of the tree. How it is going to increase the height of the tree? Let us see. So for example, we have a node with the values 7, 8, 9, 10, and 10 is the value which we actually want to insert. So we are going to split this node, 8 will go up in the up direction, and we have 7 on the left side of 8 and 9, 10 on the right side of 8. It is fine till this point, but when you say the node upwards, now we were already having 2, 4, 6 values, that means 3 values inside that root node which was earlier the root node. Now we have one more value among them, which is 8. Now if we have this 2, 4, 6, 8 situation, that means 4 keys. Now that is not the possible thing, because the order is 2. So maximum we can have 3 keys. So in that situation, this root node will also kind of get splitted, and the moment it is going to get splitted, it is going to increase the height of the tree. So 2, 4, 6, 8, the middle value, as we have taken in the previous two steps, we can have 4 as the root element, as you can see on the screen, then 2 on the left side of 4, and 6 and 8 on the right side of the 4. So now this arrangement, if you can see, this split child at the root position has actually triggered into increasing the height of the tree from 2 to 3. Now in order to we can say look into this, we will be looking into in order to understand this concept very clearly, we will be looking into one more example of this. So first of all, we need to, in order to insert elements into any of the B tree, we should be having very clear idea about the maximum and minimum number of keys a node can hold depending upon its order. So minimum number of keys will be m by 2 minus 1, and the minimum maximum will be m minus 1. Now for example, we have a tree of order m is 4. So the maximum keys will be m minus 1, 3, minimum keys will be m by 2 minus 1, ceiling of m by 2 minus 1, which is 1 here, maximum children is equals to 4 and minimum children is equals to 2. And now we have numbers which are written on the upside 5, 3, 21, 9, 13. We need to insert these into the B tree, and the calculation goes like this, that order is 4, we have order as 4. So because of 4 order, the maximum number of keys is 3, minimum number of keys is 1, maximum children is 4 and minimum children is 2. Now let us see how this is happening. Now we will keep on taking the data and inserting into a search fashion unless the node is going to reach its maximum number. So when the maximum number of the keys inside a node is being reached, the node will split into half. The median key will becomes the internal node, or median key will go up, while the left and right keys will become its children of the median key. Now let us say how it is happening. So here we have inserted 5, then comes 3. So in a search fashion we are going to insert 3 and then 5, and then we have inserted 21 also. Now the next number which is coming here is 9, but adding 9 will cause the overflow in the node, then this node must be split. So how are we going to split this node? The median key will definitely go up. So here we are taking 5 on the upside. So on the left side of 5 we have 3, and on the right side of 5 we have 9 and 9 and 21 of course. Then after that we have inserted 13 properly after the kind of split of the T, split of the node. Then we have 22 also. So, here we have 9, 13 and 21, and if we add 22, that will cause overflow in the node, hence it must be split. So, when we are going to split this node, 9 will be split in one branch, 21 and 22 will form the another branch, while the number 13, that 13 is going on in the kind of we can say next level. So, when 13 is at the next level, we have 21 and 22 on the right side. So, next comes as 7. So, 7 we can put into the middle thing. Then we have 10 apart along with the 9 we are going to keep it. Then 10 is there. So, 10 also we have we can see we have put in here. Then the situation is to put 11. So, now the proper position for the 11 is in the second we can say second child or in the middle child on the right hand side of 10. But again adding 11 will cause the overflow in the node and it must split. Now, after split, what will happen? One particular key from this node will go up. Also, we need to check that whether there is a kind of space which is available on the upside, yes or no. That also has to be seen. So, for example, we have taken the 9 up. Now, the root node is 5, 9, 13. On the left of 5 we have 3. On the left of 9 we have 7, 8 is added into the next step. Then on the left of 13 we have 10 and 11, and on the right of 13 we have 21 and 22. So, this was the situation which is being carried from the earlier situation. Now, if we want to add one more number which is 14, we can easily add in the node which is having 21 and 22, 14 is added over there. If we talk about adding 8, then 8 is added along with the 7th thing. Now, if we want to add 16, this 16 will be as per the search fashion, this 16 will be added into the last node, and this will be 14, 16, 21 and 22. So, when we talk about 14, 16, 21 and 22, 4 keys cannot be there because maximum it can have 3 keys. So, that means 16, which is going to be the middle value, is going to go up. But the problem here is the root node or the parent node is already full. So, we have 5, 9, 13 and 16, and this insertion of 16 or proclamation of 16 from the bottom level to the up level is going to kind of split the parent node also. So, we in the parent node we have 5, 9, 13 and 16, and then we are going to split the parent node also. When the parent node is going to be split, one the middle element which is 9 will go up, and then we can have two nodes, one on the left side of the 9 containing 5, another one on the right side of the 9 containing 31 and 16. So, this is going to be the 13 and 21. So, this is going to be the situation. So, we have 9, on the left side we have 5, then on the right side we have 13 and 21. We could have taken 16 also, and on the right side we have we could have taken 21 and 22. That is also a kind of finding the median value if it is an order which is even. So, in case of an even order, you can make a policy that whether you are going to take the kind of upper median or you are going to take the lower median. That is actually a policy decision. So, we have 9, then on the left side we have 5, on the right we have 13 and 21. Now, 5 left side is having 3, right side is having 7 and 8, 13. left side 10 and 11, in between 13 and 21 we have 14, 16, and on the right side of 21 we are having 22. So, this is basically, we can say, in this manner we are going to create our B tree by inserting one trees at a time. What do we need to do is, we need to keep on inserting the trees in a such fashion. Once the key reach the maximum number, split the node into the half, take a decision about the median key. If number is even, then median key will go to the up node, which is the internal, and will become the internal node, while left and right keys will become its children. Now, we need to kind of be careful, if first of all we should not violate the maximum key property, and also we need to see that when we are percolating one value from a child to the parent node may also overflow because it has reached the maximum number of keys. Then in that situation you also need to split the parent node, and the median key will become the root. Leaf node is split in half, the median of leaf node is shifted to its parent. So, this is going to be kind of process, we can say, when we are trying to insert some values inside the B tree. But here, for the sake of simplicity, we have taken a smaller orders of m is equals to 4 or m is equals to 5. But generally if we talk about, this order can be actually very large, so that a node can contain many keys, and it may result in a high branching but the low height of the tree. So, we have understood how this search is going to be performed in B trees. Also, we looked into the process of insertion. We have also in the inception of this lecture, we have also looked into the applications and advantages and disadvantages of the B tree. More to be covered about the B trees, like deletion, etc., that we will be covering in our upcoming lectures. I hope you have enjoyed this lecture. Here is a list of references which is being used for the preparation of lecture. I will see you in the next one. Till then, take care. Goodbye.